Okay, so I'm going to walk you through the second problem that I provided you on the sheet. I typed the problem into the screen. You already have it on paper. And I've taken the liberty to go ahead and draw the diagram and to find the initial velocities in the vertical and horizontal direction. So if you want to take a time, pause the video for a moment and write down the diagram and the information, you may want to go ahead and do that. Okay, so what I'm going to do now is I'm going to sort out the information that I have into horizontal and vertical categories. And I'm going to start with the horizontal stuff. So I'm going to look at the position equation, and I'm going to write it with the horizontal information. So I do this just so I can get everything laid out before I even start answering any of the questions. So in any of these projectile motion problems, the horizontal acceleration is always 0. So that 1/2 acceleration is 0, t squared, plus the initial velocity in the horizontal direction is v sub x of 0, which I stored as b. So I'm going to write that as b times t. And then my initial position is it's no distance from the starting point horizontally when it starts. So that's going to be 0. So my horizontal position equation is b times t. My horizontal velocity equation, should I need it, again, the acceleration is 0, and the initial velocity is b. So that equation is always just going to be b, which makes sense because we talked about there's no acceleration in the horizontal direction, so that velocity should always be constant. So I'm just going to mark these just in case I need to come back to them. And now I'm going to do the vertical information. Now, big deal here. When we do the position equation, like we talked about in class, notice we're dealing with feet here, so we need to use the imperial measure for gravity, which is -32. And then my vertical initial velocity was v sub y sub 0, which I stored as a. And my vertical initial position, it actually starts at 20 feet off the ground, so I'm going to go ahead and put that in as 20. If I simplify that, that gives me -16 t squared plus at plus 20. So I'm going to hold on to that. And then my velocity equation would be -32 t plus my initial velocity, which would be a. All right. Now, I'm ready to answer the question. When I set up these equations up, I can answer anything like hang time or range or any of that because I already have the equations written out. And we're actually going to use these equations a little bit later on to be able to graph the motion of this. So it's useful to be able to get them. So I'm going to actually answer the question now. So the question says, I got this ship, and this ship is 2,640 feet away. That's on a horizontal direction from the fort. So first things first, I'd like to figure out if the cannonball I launch actually reaches 2,640 feet horizontally. So that means I want to know, does this position ever actually reach 2,640? So the way to find that out is I take 2,640 and I set it equal to that horizontal position. Now you can see solving this for t would be really easy. I just divide both sides by that b. And when I do, I get 6.85 and some change, which I'm going to store as c. Now what this means is, since there's a time that actually exists where it reaches that point, it takes 6.85 seconds to reach that horizontal distance. So now I need to know if it actually hits the ship. So what I'm going to do is take this time, which is how long it took to go that far horizontally, and I'm going to plug it into the vertical position equation. Now the reason for that is I want to know how high it is when it reaches the horizontal distance that I went for the ship. Now, when I do this, if I got back a negative number from plugging this in, this would mean that the cannonball actually would be underground when it reaches, or underwater as the case may be, when it reaches the ship, so it actually wouldn't have reached the ship. If I get a positive number, it's still in the air when it reaches the ship. So I'm going to plug C in. And I'm going to do all this work on my calculator, and you may want to do the same thing. So when I plug that in, I'm going to get a number. Let me do a little click in here. It's about 866.17, blah, blah, blah. Now, that means that when the cannonball reaches 2,640 feet horizontally, it's still 866 feet in the air. The ship is only 50 feet tall. So the cannonball flies over the ship without any danger whatsoever. So if I wanted to fire another shot and have another chance of hitting the ship, then I would need to lower the angle somewhat. So I challenge you to go ahead and try to adjust the angle to something smaller than 31.2 and see if you can hit the ship on the second shot.